All right, statistics, let's get after section 7.3, estimating a proportion. This is a p-hat section. We're only going to deal with p-hats here. We might talk about the others in theory, but we're going to create a confidence interval for p-hats. In section 7.3, had a drink of water right there. Our structure for a confidence interval goes like this. Point estimate. The point estimate is the p-hat or the x-bar. In this case, that's going to be a p-hat every time. And then plus or minus what we've been calling the margin of error. Okay, so I take the point estimate, I add the margin of error, I subtract the margin of error, it gets me two numbers. I put the low one first, the high one second. And there we go. So far, our margin of error has been one of these three possibilities. 1 times the standard deviation if I want to be 68% confident, 2 times the standard deviation if I want to be around 95% confident, and 3 times the standard deviation if I want to be 99.7% confident. These came from the 68, 95, 99.7 rule that we studied all the way back in chapter 1 or 2. And the standard deviation formulas that we learned, this was in the last chapter, chapter 6, it would be n times p times q if we were messing with x, the count of the number of successes. That's the standard deviation of x right there. Well, this would be the standard deviation of p hat. That would be the taller square root of p times q over n. That's for p hat. The proportion of yeses or successes out of n responses when we change it to a decimal. And then, of course, the sigma of x bar would be the population standard deviation over the square root of n. That would be for x bar, the mean of the sample. Those are the three that we got, okay? And we would multiply how many times this standard deviation to get a margin of error. It's made of two things. How many standard deviations do you have to go? And what is the standard deviation? That's the margin of error. Now in section 7.3, we'll focus only on the confidence intervals using p hat from a sample to estimate a population proportion p. So of those three, this is the guy we're dealing with for this section right there. But since a confidence interval is built on several theories that we've studied, like a random sample, been talking about those forever now, and a normal curve, been talking about that since chapter 2, we have to verify, before we can do a confidence interval, we've got to verify that conditions that went along with these things have been met before we actually do any confidence interval work, okay? So there's page 1. We got 4 pages to do today. Here we go, page 2. Condition number 1. Before I can write a confidence interval up and say that I'm smart, I know what I'm talking about, I got to talk about condition number 1 will be called the random condition. All right, the collected data has to have come from a legit random sample. So, you have read the example given to you and you decide if the sample was random or not. The word random, I'm going to put it in quotes here. If somebody says, hey, we took a random sample, that may not be enough. We need a legit random sample that doesn't have bias in it. If someone tries to take a random sample but they don't know what they're doing, they would call it a random sample, but they could have been wrong. It could have been a convenience sample. We talked about that in class. It could have been a voluntary response sample. We talked about that in class. And people like to do those and say that they got a good response from everyone. Happens on social media an awful lot, doesn't it? If the data does not come from a random sample, preferably a simple random sample, doesn't have to be, there's other legit ways to get a sample, but there may be bias in the data. So no matter what you do, your results will be worthless, garbage, inaccurate, no good, not worth our time. That is the random condition. You got to make sure that you got a random sample. If you don't, you have bias in your data and your confidence interval will not be accurate. Number 2, the large count condition. This is also known as the normal condition. All right, here's some stuff that we have definitely talked about, including going 1, 2, and 3 standard deviations away. The 68, 95, 99.7 rule, that only applies to a normal curve. We're about to find other numbers than just adding 1, 2, and 3 standard deviations to create different confidence intervals due to, different confidence levels, but they're all based on the standard normal curve. If we can't verify that we have a normal curve in the first place for a sampling distribution, we got no business using these numbers. Now that standard normal curve has a mean of 0 and a standard deviation of 1, right? So if you're not using data that comes from an approximately normal sampling distribution, those are the things you studied last chapter. Well, if you can't say that it's approximately normal, you shouldn't use the theory based off a normal curve, so you shouldn't guarantee that 1, 2, or 3 standard deviations gets you 68, 95, or 99% confident. If a data does not belong to approximately normal sampling distribution, you shouldn't calculate a margin of error. You should stop. We have to verify conditions have been met before we use statistical inference processes, just like a confidence interval. Here's how you verify the normal or large count condition for a p hat. Fortunately, you guys have already done this. You check to see if n times p hat and n times q hat are greater than 10. If so, the sampling distribution for p hat is approximately normal. This will be known as the normal condition. We have a random condition, we have a normal condition. Let's go to page 3 and we'll find another one. Oh, no we won't. We got an example. You got to get yourself a Libro and we got to verify the random and the large count condition. So, we go get a Libro off my shelf here and we'll go to page 469. Hopefully there's a picture of an ugly, oh, no pictures whatsoever. So, we're going to do number 1 and 2. Here we go, rating cafeteria food. My girl LaToya wants to estimate P equals the proportion of all students at her large boarding high school that like the cafeteria's food. Nobody likes the cafeteria food, nobody. She interviews an SRS of 50 of the students living in the dormitory and finds that 14 think the cafeteria's food is good. Check if the conditions for calculating confidence interval have been met. Okay, the random condition is good to go because we see it's an SRS. If somebody says SRS, they know the term simple random sample. That's good enough for us. Now the p hat is 14 out of 50. Let's remember that. The random condition, this is met with an SRS. That is legit for us. Now that p hat that she got was 14 out of 50. Okay, so that's 0.28. How do you check the large count condition? You multiply together n times p hat, so that's going to be 50 times 0.28. That, of course, if I multiply those together, is going to be 14. And n times q hat, that would be 50 times, well, 1 minus 0.28 is 0.72, and that's going to be 36. You know how I know? Because these two have to add up to 50, don't they? Okay, we're going to say both are greater than 10, so p hat is approximately normal. All right, there you go. You guys have done this before. I'm going to skip number 2 because I think you're good at this, right? Okay, finding a critical value is what's on next on here. The critical value is the number of standard deviations that you add and subtract in order to create your confidence interval. It depends on the level. If you want to be 90% confident, you'll have to go a little less than 2 standard deviations. Okay? The margin of error, had to yawn there. The margin of error is made up of 2 things, a critical value and a standard deviation. Okay? So let me draw this out. Technically, this is what I wrote earlier. Point estimate plus or minus margin of error. Right? That's the number that we add and subtract in order to create the interval. Yeah? Point estimate plus or minus margin of error. It really goes like this. Here we go. Point estimate. That margin of error is made up of 2 things. A critical value is what we're going to call it. So far, we use the numbers 1, 2, and 3 if we wanted to be a 68% confident, or 95% confident, or 99.7% confident, times some kind of standard deviation formula. And for the p hats, we have that one readily available. Okay? Where we started out only using 1, 2, or 3, we're going to find more critical values than that coming up. Okay, there are many more critical values, and they all depend on how confident you want to be. Okay, so for an example out of this one that we've done so far, would go p hat plus or minus 2 times the square root of p times q over n if we wanted to be 95% confident. Okay, that's what I mean by critical value. How many standard deviations do you have to go for your confidence level? You take that number and multiply it by the standard deviation. Okay, last page. Here we go, people. Last page for the day. Quick notes. Just rolling right through them today like a boss. Find a critical value for a 90% confidence interval. I was supposed to fit percent on there, but I put my 9 in the middle of the line. 90% confidence interval. Now let's see what that means. Okay, I'm going to use the inverse norm for this. So there's 0, 1, 2, 3, 1, 2, and 3. I would like to be 90% confident. So I'm going to draw out here and out here. I'm going to say I want to be 90% confident. I'm going to use inverse norm for this on my calculator. But the problem is, inverse norm doesn't just do stuff in the middle. It goes all the way to the left, and it goes up to the number that you want. Okay, so this is going to be, I'm going to call it a z star. That's what it ends up being. But I got to figure out what's in this tail, because I have to add the middle 90 plus this here. So think about it. If there's 90% there, isn't there 10% left in the two tails added together? So isn't this 5%, and isn't this 5%? It's got to be, right? Now, I'm going to find this z. It's going to go like this. Inverse norm of, we got to put decimals in when we do inverse norm. Can't put whole numbers in there. 90 plus 5, 0.95, 0 for a mean, 1 for a standard deviation. Ready? I go second and distribution. It's in the variables part. Second variables. You've been to normal CDF and stuff like this before. Inverse norm. There it is, number 3. The area I'm going to say is 0.95. The mean is 0. The standard deviation is 1. And the tail is to the left. Not everybody gets that option. I could do 90 in the center, but I'm going to do this because everybody can do this way. Okay, and then I'm going to hit paste. And it tells me that the z I would need is 1.645. That's how many standard deviations I need to go if I want to be 90% confident. So this would end up looking like this. Ready? P hat plus or minus 1.645 times the PQ over N. Instead of 1, 2, or 3, I got to go 1.645 if I want to be 90% confident. There's a function on the calculator, inverse norm. You guys have used it before. That gives z values if you give it an area. Okay? So I think I'm going to do 2 more and we're going to call it a day. All right? So I'm just going to draw a normal curve, Put a 0 in the middle and go 1, 2, 3, 1, 2, 3. Doesn't have to be perfect, as usual. If I want to have an 80% confidence interval, So think about what that means. I want 80% in the middle. I'm going to figure out what this z is that tells me how many standard deviations I need to go in order to be 80% confident. I would like to use the inverse norm for this, but I got to remember to add the left tail. So if there's 80% here, there's 20% here. Each one is 10%, isn't it? Right? So I'm going to do an inverse norm with 90%. Here we go. Z equals inverse norm 0.90 with a 0 and a 1. Okay? So go back to my calculator. And I'm going to go second variables to get to the distribution menu. Go down to inverse norm. I'm going to put in 0.90 for the 80% in the middle plus the 10% in the tail. 90. And it's always as a decimal, guys. 0, 1. It'll be in the left. I go down and paste. This one is 1.282. Z equals 1.282. So if I want an 80% confidence interval, up here was a 90% confidence interval, right? Well, here I'm going to go, this would be p hat plus or minus 1.282. So I go just over 1 standard deviation, and it'll be PQ over N. And so that would give me an 80% confidence interval. You guys see how it works? I'm going to do one more. Ready? I'll just go down here where I got a little more room. I'm going to put a 0 in the middle, and put my 3 marks. Now I would like to do this for a 99% confidence interval. Okay, so that's going to be a bit wider. I got 99% in the middle. I need to know what's in that tail. Well, if there's 99%, there's 1% left on the outside. So this is a half of a percent, so 0.5%. And this is a half of a percent, so 0.5%. And so I've got to put into the inverse norm 0.99 plus, this would be 0.005, wouldn't it? Isn't that half of a percent, right? Okay, so this z, and by that z I mean this one right here telling me how many standard deviations I have to go to be 99%, will be inverse norm of 0.995 and 0 and 1. Here we go. Second variables, inverse norm, 0.995 and 0 and 1. All right, I get 2.576. If I wanted to make a 99% confidence interval, I want to be really confident, I got to go much further. I got to go 2.5 standard deviations. Got to go wider if I want to be more confident as a confidence interval. So this one will go p hat plus or minus 2.576 times the square root of this pq over n situation. And we're done with day 1 of section 7.3. Let's see, I've got homework for you guys to do. Can you still see on the picture? We're going to go page 469. Larson says, okay, so, and there'll be 3 through 9. There you go, people. Enjoy your day. We'll finish section 7.3 tomorrow, and then probably looking at like some extra practice, maybe kind of a open note quiz, maybe just extra practice, but we won't do anything new after tomorrow. We're going to spend some time, make sure we know what we're doing. So have a good day. Section 7.3, part 2 tomorrow.